Figure shows the graphical representation of Young's double slit experiment. As I told you in the previous discussion, that the maximum interference bands are uniformly illuminated bright and dark bands. The intensity of a bright band is equal to 4I0, where I0 is the intensity of each superposing wave, whereas the intensity of a dark band is 0. Now what is the, so this is a graph between the intensity and the path difference delta x. We know that delta x is equal to n lambda for a bright band. Delta x is equal to n lambda for a bright band, where n takes the values 0, 1, 2, 3, etc. And delta x is equal to 2n minus 1 lambda by 2, where n takes the values 1, 2, 3, etc. Which means, let us identify the positions of bright bands. So delta x, this is delta x, right? So corresponding to the central maxima, the path difference is equal to 0. Central band is a bright band in Young's double slit experiment, irrespective of the wavelength of light involved. The central band in Young's double slit experiment is a bright band, irrespective of the wavelength of light involved. Then we will get the first dark band at a distance lambda by 2. Because putting n is equal to 1, 2 minus 1, that is 2, 2 lambda by 2. 2 minus 1 is 1, 1 lambda by 2. So first dark band is at a, so I will put plus or minus, because on this side you are getting, so when you have a screen and this is the center, you will get a dark band here, you also will get the first dark band here. You will get the next dark band here, you will get the next dark band here. So that means delta x can take positive as well as negative values, so this is minus lambda by 2, and correspondingly this is also plus or minus. This is minus 3 lambda by 2, this is 3 lambda by 2, this is minus 5 lambda by 2, this is 5 lambda by 2, correspondingly this is minus 7 lambda by 2, and this is plus 7 lambda by 2. So this is the variation of the intensity in YDSC with respect to the path difference, let me tell you. Now it's an important graph. This clearly explains, so please understand this. This clearly explains the variation of intensity with the path difference in Young's double slit experiment. Now we will look into the next condition. Come on children. So we will look into the next condition for this thing. So we have studied the xn, the distance of the nth band from the central band. So xn is equal to 2n minus 1 d lambda divided by 2d for a dark band. Now we will plot graph by taking that into consideration. So xn. So I am going to plot the graph here by plotting xn. Again I will say this is plus or minus 2n minus 1 lambda capital D divided by 2 into small d. Okay, let us do it. So in this case, what I will do is, okay, so xn, and similarly xn is equal to plus or minus n d lambda divided by small d for a bright band. Here n takes the values 1, 2, 3, 4, etc. Here n takes the values 0, 1, 2, 3, etc. Now look at this condition. Look at the graph now. I am plotting on the same graph. You have to plot in different graphs, I tell you. So you have to draw separate graph to represent the same. So when n is equal to 0, you get a bright band, right? So this is the first condition. Or one more thing we can say is this is equal to what I am saying. This is plus or minus n beta, I can say, because beta is fringe width and this is d lambda divided by small d. Right, so this is beta by 2, because correspondingly this also can be written as So this is the condition for dark band, this is the condition for bright band I am writing. So this is equal to plus or minus 2n minus 1 beta by 2. So in terms of beta we are going to represent all the same, right? So this is beta by 2, this is 3 beta by 2, this is 7 beta by 2, this is 5 beta by 2, this is 7 beta by 2. Now correspondingly what is on the left side? So in xn I am representing in terms of beta. This is minus beta by 2. This is minus 3 beta by 2. This is minus 5 beta by 2. And what is this? This is minus 7 beta by 2, right? So these are the variation of the intensity in terms of the distance from the central band. So in YDSC, the most important point you have to understand is that the central band is a bright band irrespective of the wavelength of light involved. Now we will move to the next condition. So we have learned that in the previous discussion, path difference is equal to A sine theta, that is equal to n lambda, where sine theta is equal to xn by d, we have proved in the previous video. Now I can say this is approximately theta. Theta, because as I told you, since xn is much smaller than d, xn is very small compared to d, so sine theta is equal to xn divided by capital D is approximately theta, which implies sine theta is a very small angle, so A theta is equal to n lambda. Now theta is equal to n lambda divided by A. So this is the condition for obtaining a bright band. This is the condition for obtaining a bright band. Then what will be the condition for obtaining a dark band? Now I want you to write by yourself. Think about it for a minute. For a dark band, this is 2n minus 1. Sorry, not A, it is D. Not A, it is D only. 2n minus 1 lambda divided by, this also is D, lambda divided by 2D. Theta is equal to 2n minus 1 lambda divided by 2D. This is the condition for a bright band, and this is a condition for obtaining a dark band. Here n takes the values 0, 1, 2, 3, etc. Here n takes the values 1, 2, 3, etc. Right? N takes the values 1, 2, 3 here, n takes the values 0, 1, 2, 3 here. So be careful in choosing the values of n for a bright band and choosing the value of n for a dark band. This is very important, I tell you. So be very careful in choosing these values properly. Right? So hope it is clear to you. Now we will move to that aspect into the graph. We will inculcate that idea into the graph. Yes. So I'm going to plot in terms of theta, in terms of angular width. Theta n. So this is theta. I'm going to say first dark band. So obtain that lambda divided by 2d, right? Minus lambda by 2d. 3 lambda divided by 2d. Minus 3 lambda divided by 2d. 5 lambda divided by 2d. Minus 5 lambda divided by 2d. 7 lambda divided by 2d. Minus 7 lambda divided by 2d. So these are the values we are getting, right? So these are the values we are getting for the angular fringe width. So in terms of theta, angular width of the nth maximum, nth minimum. Now from here, one more thing we can easily find out just by looking at this equation. So what is that I am going to get is angular fringe width. Angular fringe width. So what will be the expression for angular fringe width? Angular fringe width theta is equal to, angular fringe width theta is the distance between consecutive dark band. Correspondingly you can say it will be the distance between consecutive bright bands as well, right? It's the distance between consecutive dark bands, or it is the distance between two consecutive bright bands as well. So you can easily get it. Come on guys, you just get me the answer fast. So this will be lambda divided by d. This will be 2 lambda divided by d. You can see that the difference of these two is lambda by d. That is one way of getting this answer. The other way of getting this answer is look at this. This is lambda divided by 2d. This is 3 lambda. This is 1.5 lambda by d. This is 0.5 lambda by d. Simply we can say this is also equal to lambda divided by d. What is lambda? Lambda is the wavelength of light used. Wavelength. So lambda is the wavelength of light involved. And what is small d? Separation between the slits. Small d is the separation between the slits and lambda is the wavelength of light involved. Ready? So what is lambda? Lambda is the wavelength of light involved and small d is the separation between the two slits. It's so simple to understand, guys. It's not at all a difficult thing at all. I hope this much part is absolutely clear to you. Now we will move to the next concept. The shape of the interference bands in YDSC. Shape of the interference bands in YDSC. Now it's a very important question because most of you make mistake in entrance examination. We got path reference S2P minus S1P is equal to n lambda. This is a condition for constructive interference. Or S2P minus S1P is equal to 2n minus 1 lambda. Right, so this is the condition for destructive interference. Now what are be the conditions? So for at a particular point on the screen, comma, this path difference is equal to a constant, right? At a particular point on the screen, this particular path difference is a constant, right? So here n is called the order of the fringe. Here n is equal to 1. Here n is equal to minus 1. So if you take these 2 points, the path difference is a constant, right? Path difference is a constant. So in this case, what you are going to get is, so path difference is a constant, that is S2P minus S1P is a constant. At another point, it's a constant but a different value, you say. So when S2P minus S1P is equal to a constant, the locus of all points, not locus, I'm sorry, locus of all points satisfying this condition, locus of all points that satisfy this condition, as you know in mathematics, x(x1) minus y(y1) is equal to a constant. That's equation of what? It's equation of a hyperbola. So locus of all points which satisfy this condition will lead to what is called a hyperbola. So question is, what is the shape of interference bands in Young's double slit experiment? If you ask me such a question, my answer to that question is, it is a hyperbola. So generally for that, for small values of capital D, the graph is hyperbola. However, if D increases when capital D, what is capital D? Capital D is what? Capital D is the distance between the slit and the screen. So hyperbola, as you know, this will be the shape of the graph. This will be the shape of a hyperbola. Now when capital D increases, what will happen to this hyperbolic nature? So hyperbola becomes linear, right? So on increasing capital D, so generally if you ask me the question, what is the shape of interference bands in YDSC? Correct answer is hyperbola. Now on increasing D, this hyperbola changes to what? So when capital D is increased, the hyperbola will changes to straight interference bands, let me tell you. So it will become straight bands we are getting. So when capital D increases, hyperbola changes to straight line. But if you get a question, what is the shape of interference bands in YDSC? Your answer has to be a hyperbola. Because straight line is just only a case of this, I have to conclude. So we will move to another topic now. Optical path. So next topic that we are going to consider is optical path length. Optical path length. So let me consider a medium of thickness T. And the refractive index of this medium is N. Now what happens is that light is incident normally on this medium. When it is incident normally on this medium, it will pass without any deviation and it will come out likewise. Okay, so I am taking, now instead of T, I am taking D. Now I can say the time taken to travel a distance D is equal to V into T. What is V? V is the velocity of light in that medium. Velocity of light in that medium. So D is equal to Vt, and I can say V is equal to C divided by N into T. C divided by N into T. So C divided by N into T. What is C? C is the speed of light in vacuum or in air. Speed of light in vacuum. Right, so from here I can say CT is equal to N into D. What is CT? What is CT? It is the distance covered in air, right? C is the speed of light in air. T is the time taken to cover this distance in the medium. So T equal to 0 and it reaches here at a time T is equal to T. So my question, what is CT? CT, come on. In Korean, you can say the answer. No, not at all. What is CT? It is the distance covered. C is the speed of light in vacuum or air. T is the time taken to cover the medium. So I can say CT is distance covered in air by the time, right, so come on, what will be that? By the time it covers a distance D in medium, right? By the time it covers a distance D in medium, right? It's a distance covered in air. By the time it covers a distance D in the medium, right? Yes. So therefore, this distance is equal to N into D, right? Now I am calling this CT by the name optical path. CT is called optical path. So my question, how will you define the optical path equivalent to the medium? Optical path equivalent to the medium is, okay, optical path equivalent to the medium. I am writing here, optical path is equal to path in medium into the refractive index of the medium. So optical path is what? Is a path in medium multiplied by the refractive index of the medium. Okay, so to make it more clear, so let us read the definition once more. Distance covered in air. So CT is the distance covered in air by the time it covers a certain distance D in the medium. Okay, let us understand this idea. So considering two lights coming here. So this is one light that passes through the medium. The other light I am going to show with another color. So now the light, this one comes here. So the first light which reaches here at a time T is equal to T. By the time, so this is the next radiation. So these two are parallel radiation, both reaches here at T equal to 0. Now how much distance this ray will travel when this ray is here? I should say it will be more than that. If I say this distance is equal to D dash. So D dash is equal to C into T, right? D dash is equal to C into T. That is the distance traveled in air by the time it covers a distance. And correspondingly, distance D is equal to CT. So this ray is now here only. The other one has reached here. Sorry, this is not CT, it's VT. So I can say VT is equal to CT divided by N, where N is the refractive index of the medium. Right, so now CT is equal to D dash. So I can say from here, CT is equal to D into N, right? So this is N into D. It's equal to N into D. So D dash is equal to CT and CT is equal to N into D. Right, so my question. In this case, if this side says ray 1 and this is ray 2, what is the path difference here? Path difference here. Path difference. In this case, what will be the total path difference caused? I would say this is equal to. So D dash is the distance covered in air by the time. This is time D equal to T. So difference in path. This is the path traveled in air. This is the path traveled in the medium, right? This is path traveled in the air in time T. This is the path traveled in air in time T. This is the path traveled in medium in time T. I repeat. What is this? Come on, all of you listen properly. This is the path traveled in time T. This is the in where? In where? This is the path traveled in time T where? Where? It's a path traveled in time T in air. This is traveling in air. Right? So, and this is traveled in the medium. And this is equal to D. This distance is D. The other distance is D dash. Path difference should be equal to D dash minus D. D dash minus D. Both reaches here at the same time, right? Both are here because here it was both are traveling in air. So both are here at T equal to 0. But at time T is equal to 0, T, the second ray is here. The first ray is only here. So this much is the path difference, right? Path difference is this much, which can be said as D dash minus D. But what is D dash? D dash is equal to CT. CT is equal to ND. So ND minus D. This is equal to N minus 1 into D. So in this case, the path difference created is equal to how much we are getting? It is equal to N minus 1 into D. Now what is the significance of learning optical path in our situation? Let us consider a problem using that with Young's modulus. Young's double slit experiment. Okay. These are the two slits I am considering. And this is a source which is kept symmetrically with respect to the slits. Now this is a screen, forgive for the drawing mistakes. Now here, as you know, that this is the center of the interference pattern, YDSC. As we have learned in the previous video, here the path difference is equal to 0, right? Why? Because this is S2, this is S1. As we already know that SS1 is equal to SS2 and S1C is equal to S2C. The question now arises is, what happens if I place a transparent sheet in the path of one of the waves? So I'm going to keep a transparent sheet here. I'm going to keep a transparent sheet here. So if I place a transparent sheet here, what happens is that now the path difference. So already I told you, capital D. This is small d. Capital D is much greater than small d. That means S1C is parallel to S2C, right? S1C is parallel to S2C. If I draw this diagram, now let me take this thickness is equal to T. Thickness I am saying T, not the time. The thickness of this transparent sheet is T. Now, which we can say that this is S1 and we got a transparent sheet in between of thickness T. And this is S2 and both are meeting at the point C. So, introduction of this one will surely create a path difference as we have just seen now. So, in this case, what will be the path difference? So distance. So if I say this reaches at time 0, this reaches at a time t is equal to t1 time. This reaches at a time t is equal to t1. Obviously, as we have learned from the previous discussion, the introduction of this slab will create a path reference. If I say this time interval is t1, time interval is t1. So in this case, the path reference is equal to nt minus t. As we have seen just before. This glass slab will create a path reference. Sorry, not glass slab. The transparent slab will create a path reference. So here it will reach faster than what it is reaching here. So a path reference will come into play here, and that path reference is nt minus t, which is n minus 1 into t. Now, can we conclude that this point is a bright band? I can't say. Okay, I will take, instead of n, we will take mu as the refractive index, because n we have already represented as the order of the fringes. So mu minus 1 into t is the path reference created here at the center, at the original center. Question. Then, where is the point of zero path reference? Where will be that point of zero path reference? So as to compensate for the path reference, so this will be shifting its position such that I am going to get another point where the path reference is equal to 0. So it will be shifted to this position, right? It will be shifted to this position. Now this will be the position where the net path reference will be 0, because in order to compensate for the loss of time, it will bend towards a normal. So it has to shift towards this direction. Let us say this shift is, say, x dash. X dash is the shift created in order to minimize the path reference. So in this case, the path reference is mu minus 1 into t at the center. So the ray will shift towards that side where it will, the central maximum, that is c dash. The new central maximum will be shifted towards that side where this transparent sheet is placed. So let us say that distance is x dash. So x dash is equal to n lambda capital D divided by small d. I am considering that's a bright band because central band is a bright band. So as the central band, as I said, it is shifted, which means I have to get a bright band here. This should correspond to a bright band, I am saying. So x dash is equal to n d lambda divided by small d, right? So what I can say here is, or what we have learned is that path reference. Path reference is equal to small d into xn divided by capital D, as in our discussion. As in our discussion, we have learned that this is small d into xn divided by capital D. Right? Sorry, that's a path reference. Yeah, right. That's a path reference because d sine theta is the path reference. So d into sine theta is xn divided by d. That is a path reference. So path reference is equal to that much. From here, what I can say, this is equation number 1. This is equation number 2. Now we need to equate equations 1 and 2 because left side of both are same. Which implies mu minus 1 into t is equal to d into xn divided by capital D. Right? Mu minus 1 into t is equal to d into xn divided by capital D. So from here, what I'll get? From here, I will get xn is equal to mu minus 1 into t into capital D divided by lambda. What is the formula for beta? Beta is equal to d lambda divided by, no lambda here, it is small d. D lambda divided by small d is the expression for beta, right? Beta is equal to capital D lambda divided by small d, or this gives you capital D divided by small d is equal to beta divided by lambda. It is beta divided by lambda, which gives me the shift is equal to xn is equal to what I am going to get? Mu minus 1 into t into beta divided by lambda. Right? Oh, sorry, I still made one more mistake. This is not capital D, small d divided by capital D. Right? Or no. It's capital D divided by small d. Yes. So xn is equal to the distance of the n, the number of the total distance through which the band shifted is mu minus 1 into beta divided by lambda if you are given fringe width and lambda in the equation. So that is the equation we have to get. Now one more thing we can do from here is that since xn is equal to n beta, since xn is equal to n beta, I can say n beta is equal to mu minus 1 into t beta divided by lambda. Now this will give you the number of fringes that undergone the shift. Number of fringes undergone shift. Number of fringes that has undergone the shift. The number of fringes that has undergone the shift is n is equal to mu minus 1 into t that divided by lambda. So this is the number of fringes through which the central band has shifted. From the center. This is from the center. The number of fringes that has undergone shift from the center is given by n is equal to mu minus 1 t divided by lambda. So this is the number through which the central band has shifted in the process, right? The number of fringes through which the central band has shifted is this much in case of introducing a transparent sheet in the path of one of the interfering beams. And towards which direction it has shifted? It has shifted to that direction, or it has shifted to that direction in front of the fringe where you have kept the transparent sheet. So this is an important thing to be understood regarding Young's double slit experiment. Very, very important I am saying. So regarding the Young's double slit experiment. Okay.